Now we have Lu Chu and Shawn here to guide us through the CV model training using PyTorch and Alluxio on Kubernetes. And ready to dive in, Lu and Shawn?
Oh, hi, Sense Hope. You guys see me and all of the slides here? Oh, now maybe I need to share the screen. Sorry, just some minutes. So before sharing that, so today we'll get some demos about the CV model training with PyTorch and Alluxio on Kubernetes. And here, Shawn and I will co-present this talk. And I am the machine learning engineer and the Alluxio PNC maintainer here at Alluxio. So I'm mainly focusing how to integrate Alluxio with AI machine learning. And I also have Shawn here. So hopefully you can see him. So Shawn is our software engineer at Alluxio, who is focusing on the integration with Alluxio and Kubernetes. So now we will continue our talk. So today's agenda will focusing on 4 aspects. We will have a quick recap of Alluxio in AI machine learning stack because there are so many talk about this aspect. So we will keep it short. And we will have 3 demos. One is about the computer vision model training, an end-to-end training demo. And another one is a data loading performance demo, which benchmark against Alluxio vs some competitors. And also lastly, but not leastly, like we have Alluxio on Kubernetes demo that can tell you how to launch Alluxio on Kubernetes and also how to use Alluxio and also visit our really fancy dashboard. And now we will continue. So for the first one, Alluxio. So Alluxio kind of sits between the machine learning frameworks like PyTorch, TensorFlow, some model training and inference framework, and our storage systems like S3 and other storage systems. And Alluxio helps the offline training platform to fetch data from remote storage and catching it to speed up future data access. And on the other hand, Alluxio helps catch models so that we can speed up the data deployment process. So here is the demo that we are going to do today, which is a model training demo with Alluxio. You can see in the middle that we have a Kubernetes cluster, which has some GPU instances. The GPU instances doing some actual model training. We interact of those model training with our interactive notebook on Jupyter. And we also have an Alluxio cluster deployed. This Alluxio cluster is launched using Alluxio operator, which Shawn will give more details later. And in the middle, we can see that Alluxio helps fetch and catch data from S3 remote storage. So we fetch the data set stored in Alluxio and then provide those data set to our training workloads. And the providing part using 3 main APIs, the POSIX API, RESTful API, and S3 API. So for POSIX API and S3 API, it targets for the user-friendly use cases. Basically, if your training script are originally using local folder format, you can switch to your S3 storage still using a local folder. That's provided by Alluxio POSIX API, which turns your remote storage system, your remote storage data set to a local folder format. And you can also utilizing Alluxio's S3 API if your training script is built on top of the S3 dataset directly. And also like some other users, they prefer to use RESTful API, especially some advanced users, which the actually RESTful API is fully controlled. So it doesn't need to implement some local or S3 interface. So it maximizes the performance and have more controllability on top. So this is Alluxio's 3 main APIs so that the users, they can directly use their remote dataset without the need to change their training scripts. And on the right side, we have 2 fancy dashboards. The TensorBoard, which is the training visualization dashboard. It helps us to tell some key training metrics. The first one, the data loader time. How much time is actually needed and actually used to loading data from the storage. And the other part is the most key metrics, the GPU utilization rate, which helps to know that did we fully utilize our training machine resources? And on the bottom that Shawn will give more details on is about Alluxio dashboard. The Alluxio dashboard helps us to know that how many of the API calls and the read calls are provided by Alluxio and is cache hit, and how many is not cache hit and actually need to fetch from remote storage. And by knowing how many of calls are provided by Alluxio, we can calculate that how many API calls basically we are saving from calling S3 and have some cost saving analysis. So first, we will give the end-to-end AI model training demo, which is the computer vision model training. And you use the most popular like ResNet-50 algorithm. And the dataset is also the well-known ImageNet dataset. And for the dataset loading, for this time, we choose the POSIX API, which is the field solution, which turns our S3 dataset into a local folder format. Oh, now we are going to show our demo. And first, let me try to make sure the quality is high so that people can see clearly. So this is our interactive Jupyter notebook, which users can follow it step by step to do the model training and see how it can interact with Alluxio. So the first several part is pretty standard. Standard data loading, standard checking device, and the session 1 is about the data preparation, which we use fields to mount the S3 dataset to the training node. And users can basically load dataset from Alluxio as if they are on local disk. So for here, there is a dataset path, which is a local path, basically the anti-Alluxio fields and your ImageNet dataset. And the other part are standard data preparation, like how you define the transformer and how you actually create the image folder dataset. We can see here the dataset image folder directly takes the root as the local path that we provided, the Alluxio fields mount part, and we provide to the Torch data loader. Both is exactly the same as you are using the local folder. And we set up the ResNet-50 models. We provide some PyTorch providers so that we can later on visualize some of the metrics like the GPU utilization rate on TensorFlow. And we also prepare the model training, which it iterates through the whole dataset and do the actual ResNet-50 training. And finally, we save the model. And now, after we have some basic understanding of the whole process, we can just follow it step by step. Yeah, do some import, check the device, use the Alluxio local folder as a dataset, and using standard Torch image folder way of loading the local image folder, and also do the profiling and the model training. Yeah, just basic standard way with a local folder here. And finally, do some model training. And we just speed up because the training takes some time. We don't want you guys just blindly like waiting here. So you can speed up and then see like how many apples we do and also the time is spent for doing each apple. And the training is finished. And finally, we save the train model. After the training is completed, because we enable the PyTorch profiler, so now we will just open the TensorFlow to browse those matches. And as you can see, this is a pretty typical TensorFlow, which has some key matches showing here. The GPU utilization rate, we can see that it's more than 90% of GPU is utilized for actual training. And also we can see the data loading time percentage is really low, it's less than 1%. And here we also have a tensor bar that later on Shawn will dive more detail into. So it basically showing that how many of the calls it actually catch heat is served by Alluxio instead of served by remote S3 storage. And what's the actual cost without Alluxio and cost with Alluxio? And what's the cost saving that you actually save in your workload when you are using Alluxio? So it's kind of estimation value based on some S3 API cost. That's the model training part. Now we will turn to another demo. Yeah, so basically, we also do this end-to-end training, not just with Alluxio. We also do it with S3 FS Fuse before, which is the most popular S3 Fuse solution, which turns S3 into a local folder format. And by comparing these two, originally when using S3 FS Fuse, the data loading rate is actually 82%, and the GPU utilization rate is only 17%, which means that the data loading from source part actually lowered the GPU utilization rate and made the GPU instance have a lot of resources wasted. But after using Alluxio, the data loader rate is reduced from 82% to less than 1%, and the GPU utilization rate is increased from 17% to 93%. Now we will move to our next demo. As we said before, that the previous demo is an end-to-end training demo. It do the actual training. So it's hard to actually make the data loading direct comparison because training is involved. And for this demo, we're basically doing exactly the same thing as end-to-end training, but we remove the training part from the benchmarks so that we can directly compare the data loading performance between the three solutions here: Alluxio Postgres API, S3 FS Fuse, and also the S3 official Python API, the Bottle 3. Yeah, another video showing our data loading benchmark. So as we said before, it's similar that the first session is about preparing the benchmark, and the things are pretty similar to before. But it said that for our benchmark part, which benchmark, you can see the benchmark part here. The benchmark data loading part. Compared to before, for this time, we did a little difference. For each epoch, we traverse the whole data set. But what is different from before is that we didn't do actual training logic. Instead, we're recording how many seconds it actually takes for us to loading one run of the data set. And then we print the duration numbers. And the session 1 is about the benchmark, and session 2, 3, 4 are just that we run the same benchmark against different data set. The Alluxio data set and the S3 FS Fuse data set, and also the S3 Python API data set to actually see what's the data loader performance between these three. So for here, the session 2 is about we run the benchmark against Alluxio data set. The Alluxio data path is just a local path, similar to what we did in the end-to-end training. And we use image folder and benchmark the data loading. We can see that the performance is kind of consistent. It's around 50 seconds to read the full data set for once. Yeah, we finished the data loading here. And now we move to the S3 dataset. The next one is using S3 dataset via S3 FS Fuse. S3 FS Fuse is the most popular S3 Fuse solution. It also turns S3 into a local folder format. And we can see that the training, the data loading actually takes much longer. Is that the first epoch? The following epoch, even local metadata and data cache is enabled. It still takes more than 200 seconds for one epoch. And the whole data loading time is like 10 times difference. And now we run the same benchmark against S3 dataset via Boto3 S3 Python API. And for this part, you actually need to modify your training script by defining your own image dataset and define your data loading logics using the Boto3 API. And for here, we use the S3 image dataset and then do the training, do the data loading. We can see that for each epoch, the time takes much longer because every operation needs to actually go to S3 to do metadata listing, to get metadata information and get the actual data. It's actually much slower than S3 FS fields and much slower than the Alluxio solution. Okay, now we will jump to our next. Yeah, so basically for the computer vision data loading benchmark against Alluxio, S3FS fields, and Boto3 S3 API. Alluxio is 5 times faster than S3FS fields here, and more than 10 times faster to the Boto3 S3 API comparison. Now I will pass it to Shawn about to do some live demo on Alluxio on Kubernetes.
Hey everyone, today I'm going to show you guys a live demo of deploying and managing Alluxio on Kubernetes cluster. So first, we developed an operator for the deployment of Alluxio on Kubernetes. The operator itself can be deployed via a Helm chart. And the reason why we use this operator, the first is it will be very easy to deploy Alluxio on Kubernetes. All the configurations are in one file, and only few commands you can have a fully ready Alluxio operator to serve your workload. And the second reason is because of the permission. Because for security reason, not all Kubernetes end users have full permission to create resources on Kubernetes. For example, you can imagine if there is a lot of users, and if they all can create pods or deployments on the Kubernetes cluster, it will be very, very hard to manage all the resources. So it's very common to see the end user doesn't have, for example, write permissions. But with operator, because everything, including Alluxio cluster, is a custom resource, if we give the specific role that has the permission to only operate this custom resources to any users, we can bypass this permission problem. So the way to create a Alluxio cluster on Kubernetes is there are 2 steps to do this. Let me show the terminal here. One second. So first, we define a dataset resource. So here you can see this is our custom defined resource. We'll give it a name, and we can specify where is your data this remote address of your dataset. For example, this is a S3 bucket, and also give the credentials here. Of course, we are not only limited to S3 here. We can also do Alluxio can be connected to all sorts of remote storage, including S3, including GCS and Azure, or local files. The local will be for the case of NAS or NFS. And then we also have we submit this custom resource to the Kubernetes API server, and then it will forward this creation request to our operator, which will in turn save this information inside the Kubernetes cluster. And next step, we'll have the configuration for Alluxio cluster. So here we specify what dataset we are using, the image, or the configuration for Alluxio, and the resources for different components of Alluxio, including CPU, memory for master, worker, and fuse, which is the POSIX API. So we also submit this custom resource to Kubernetes API server. Similarly, operator will receive this request and create the Alluxio cluster for us. And right now, we do have a running Alluxio cluster on the Alluxio cluster on this Kubernetes, and we can show it here. So we have the Alluxio worker pods running and the fuse pods. Okay, so that's for the deployment part on the Alluxio on Kubernetes. And now let's take a quick look at our POSIX API. So here, this is a node inside the Kubernetes cluster, which has fuse pod running. So if we go to this specific pods where the Alluxio fuse is mounted, so this is exactly what this bucket looks like. We have this open source dataset called Coco dataset. And we can see all these images. And we can also do an ls here. So to show some other common, so you can see this looks just like a local file system. And if I like don't prove to you, you might think of maybe this is like not actually in Alluxio, maybe it's just local. And let's we can also do something like copy. We probably turn on the metadata cache, so it might take a little bit time for it to realize that we have created this new file. Okay, here it is. Okay, so to use, so if you are, this is operated on the host machine. If you want to say your training is in a pod, you can simply mount this path into your training pod, and thus you're inside your training pod, you can see the exact same thing here. Now let's talk about the dashboard. So here we have a comprehensive dashboard to monitor the different aspects of our running cluster. This is the exact same cluster I just showed earlier. So you can see we have the current Alluxio status. We have 2 ready workers. In total, we have 8 terabytes of disk space, cache space, and currently we're using 580 gigabytes. So we have loaded 580 gigabytes into Alluxio. And we can also see the cache hit rate here. That's the percentage of data cache hit on Alluxio. Here we have more details about how the data is distributed inside Alluxio cluster on different workers, like cache space used, cache space available per worker. And we have some other debugging purpose dashboards, including the CPU load and the GC status. So if anything is wrong, we can directly accessing this dashboard to see if there's too much load or there's network problem and stuff. So it's much easier to see what's going on and to mitigate the problem and get back to normal faster. Even if everything is running smooth, we can also use all this dashboard status to see if we can distribute the data a little bit better so that the requests to data can be evenly distributed on different workers so that we don't have a very hot worker that is serving a large percentage of data while other workers are just idle and under very little load. Last but not least, we have this cost saving dashboard that we saw earlier in Lu's presentation. On this dashboard, we can see how many API requests we have is on cache hit. And we can also, depends on all this information, we can calculate how much money we saved from this cache hit. So this is very helpful. You get to show you that how Alluxio can help with your cost saving. All right, that's everything on my side. And now we are in the QA.
Thank you, Lu and Shawn. We have a question here from Diyu. Why Alluxio is faster than S3 Fuse, and since they are both using local disk for caching?
Yeah, thanks, Diyu. So in our benchmarking, so firstly, we actually give the 2 parts enough cache, local metadata and data cache for both. So it's a fair comparison. And as for the performance is better from Alluxio 2 to now our newly Alluxio 3 or Alluxio AI products, we actually do a lot of optimizations. So first, one part is that we try to remove all the locking in the reading path while ensure the correctness. We want to support as high concurrency as possible, at least in the Alluxio phase. Fuse phase, we may not be able to control that, but in Alluxio, we remove many of the concurrency bottleneck. That's one part. And the other part is that we, especially in recently Alluxio 3, we analyzing a lot of the Alluxio traffic patterns. So our users, they are really good. They share us their logs, the detailed logs about their traffic pattern and their data set to me. So we are able to do a lot of optimizations based on the traffic patterns, especially in the computer vision training, in the NLP. We collect those information and then do the kind of the read pattern change in Alluxio. So for one example is that we found that position read is actually probably faster than streaming read, and the AI read have a lot of like seek operation, etc. So we implement Alluxio position read. But to ensure the performance good, we also implement some of the smart reading mechanism on top. For example, if we feel that, oh, you read data sequentially, we will pull it for you. But if you didn't read sequentially, you kind of jumping around, especially in the structured data, then we directly help you to jump around without too much prefetch, without too much like read enlargement. And I think in this specific case, in the computer vision training part, I think concurrency, read concurrency optimizations may contribute for most part. But for the natural language processing training, the position reader and the smart read mechanism actually helps most. Yeah, answer the question. Any follow-up question? Okay,
thank you. Yes. Thanks for the question, Dee, and thanks so much for the presentation, Shawn and Lu.